Hi Margaret, I have a few slides here. I gave you a problem last time to work on, an ICE table with this reaction at the top in red. I gave you initial concentration and then the final concentration of the I2. Pretty much this involves just setting up the table and putting the numbers in the right position. So if the initial concentration is 0.02 molar, because the stoichiometry is only 1, you do minus x for that compound and then plus x and plus x on the other side. The problem gave you I2 was 0.0035 molar, and so if you plug everything in, if that's the x, you solve for Kc and you get a number of 7.4 times 10 to the minus fourth. The final concentration is just going to be whatever you calculate in this last line, stick in the x's, and those are the answers I got. For the next one, this one's a little bit more involved, and you'll see this in a second. So at this very high temperature, 425 degrees, the Kc is 55.64 for hydrogen gas, iodine gas, giving 2 HIs. If you place 0.13 moles each of hydrogen and iodine in a 25-liter flask, what are the final concentrations of everything? So the first thing you have to do is to have the proper number for the initial conditions, and we usually do this in molarity. There may be some problems later in the semester where you do moles, but for now we're going to do molarity. So I did 0.130 moles divided by 25 liters. I got 0.0052 molar, and so those were my two initial concentrations. Again, the stoichiometry is easy, so you just do minus x, and then plus 2x. Don't forget, because of that 2, you need to do plus 2x. So here's my equilibrium line. This is the information that ends up in the K expression. So it's products, which is 2x, squared, don't forget the squared. I know the 2 seems like it shows up twice, but that's the way it works. And then in the denominator you have 0.0052 minus x times 0.0052 minus x. So that's a nice coincidence that actually makes the math a little easier, because you'll notice if you take the square root of each side, you don't have to multiply out this polynomial. So if you take the square root of each side, you get the square root of 55.64 is equal to the square root of that whole expression. So if you just get rid of the squareds and solve for x, you get the value of x is equal to 0.0041. I'll save it to you to do that math out on paper so that you see that it all works. I'm pretty sure it all works. So here's your turn. At a different temperature, the Kc is 33 for this reaction. If the initial concentrations are 0.00600 molar, what are the final concentrations? So it's similar to the last one, but it's got some new math. All right, let's do something different. You probably did this in class. Sometimes you have to use the quadratic formula. So suppose you have PCl5 in equilibrium with PCl3 and Cl2. The Kc for this reaction is 1.20. The value of the Kc actually helps tip you off whether or not you're going to use the quadratic formula. This is a relatively large value, and you'll see what I mean in a minute. So if you start with the initial concentration of PCl5 is 0.0920 and then do minus x, and plus x, I get this expression for the Kc. I get x squared over 0.0920 minus x is equal to 1.20. If you multiply that out and rearrange, you get a squared polynomial. So this is where you use the quadratic formula to solve for x. Now, I don't know if your teacher allows you to do it on your calculator if you're in a test, but if you aren't allowed to do it on the calculator, you have to learn how to do it longhand, and there's a formula that you should memorize to solve for x. Now, whenever you solve the quadratic formula, you get 2 roots. You get, in this one, 0.08586 and negative 1.2. The negative 1.2 doesn't make any sense in this problem, because that would imply you have negative values of concentration, and that doesn't make any sense. So only the realistic one, I'll write that here, it's the realistic root. Only one of them will be realistic. If I plug that in, I get a final concentration of PCl5 is 0.0061, and the product molecules are 0.0859. You can always double check this by plugging these into the K expression to see if you get the number that you were given at the beginning. Now sometimes you're allowed to make an approximation. So what would I write here? Although whenever you have a quadratic equation to solve, you can use the quadratic formula, sometimes an approximation can be made to simplify. So for this one, I've got iodine, I2 gas, in equilibrium with 2 iodine atoms. So I've got 0.45 minus x plus 2x. Notice that the Kc value is very small. This is going to be useful, especially when we get to acids and bases, because by the math, if K is very small, the calculated value of x ends up being so tiny, it's just a really small change to the value 0.45. So you could basically pretend that that minus x doesn't even exist. You can't adjust anything on the top because that value isn't being compared to anything. But here, it's being subtracted from a much larger number. So in blue, you see that you could rearrange it into this, and if you solve for x, you get 7.94 times 10 to the minus 7th moles per liter. Now there's a rule that says if that value is less than 5% of the number it's being compared to, that's a good approximation. And this is clearly less than 5% of 0.45. So your final concentration of iodine is 0.45. Final concentration of iodine atoms is 1.59 times 10 to the minus 6. So I have a couple here for you to do. The first one, notice that the Kc is very big, and notice for the second one the Kc is very small. Once you do those, and we could talk about it, you probably aren't going to look at this before you do your test tonight, but I really wish you good luck on your test. Bye.